7 is questions about gaseous equilibria. Explain how figure 1 shows that the forward reaction is exothermic. So if the forward reaction is exothermic, increasing the temperature will, at a higher temperature, as forward reaction is exothermic, increase the temperature is going to shift in the endothermic direction to reduce the temperature. In this reaction, this point, we've got a higher yield at lower temperature. It's quite obvious, and therefore equilibrium has shifted forwards, right hand side, in the exothermic direction to oppose the decrease in temperature. And how do I know there's a high yield at lower temperature? Because look at this, 600 Kelvin, 300 Kelvin. That's the percentage yield. 600 Kelvin. This is the percentage yield. This is percentage yield at 300 Kelvin, and this is at 600 Kelvin. And you can see that the percentage yield at 300 Kelvin is always greater than 600 Kelvin. So a higher yield at lower temperature. Equilibrium is shifted forward, right hand side, exothermic direction, oppose the decrease in temperature. 7.2. Stay with the forward reaction. This equilibrium results in an increase, decrease, and no change in moles of gas. It's going to be an increase. Reason being, as like before, we had a higher yield at low temperature. We've got a higher yield at lower pressure. So equilibrium has shifted forwards to the side with a highest moles of gas to oppose the decrease in pressure. Explain why using a catalyst has no effect on the percentage yield. This is a really nice question, really tricky question as well, and it's very specific, because a catalyst increases the rate of forward and reverse reactions equally, so therefore it has no effect on the percentage yield. Increases the rate of forward and reverse reactions equally. 7.4, 7.5, and that's it. 7.4. Count the amount of moles of ammonia present in equilibrium mixture. We're working with Kc, so Kc square bracket. So let's construct the Kc expression. So Kc equals products over reactants, so products in square brackets, remember, square brackets imperative, NH3 for Kc, NH3 squared over H2 cubed N2. We're trying to find out the moles of ammonia present, so we need to rearrange it to make ammonia the subject. So okay, so rearrange to make ammonia the subject. We know this is the volume of the equilibrium mixture. It's already given us the correct units, and now we need a bit of thinking. We've got the equilibrium moles of hydrogen and nitrogen. We know, or we should know, moles is equal to concentration times by volume. Therefore, concentration is moles divided by volume. That's what we're trying to find out. We need to find out the concentration of ammonia first. So concentration, we can't just work out the equilibrium moles directly. So concentration moles divided by volume. So NH3 squared, well actually NH3 equals square root of Kc 0.118 times by the concentration of H2 squared. The concentration of H2 squared is going to be equilibrium moles 0.0285 divided by the volume, moles divided by volume, 0.150 dm cubed, and that is cubed, and then times by equilibrium moles of nitrogen, 0.0870 divided by 0.150. I get 0.18 times by 0.0285 over 0.0285 over 0.150 cubed, that's for hydrogen, concentration of hydrogen, times by 0.0870 divided by 0.150, and that will give me, and that's obviously square rooted because ammonia squared, we want to find out just ammonia, so we need to square root it, so we get NH3 in square brackets, the concentration of NH3 equals 0.02166. Now let's look back at that equation. I rewrite it again. Moles equals, we rearranged it, moles of concentration, volume, concentration, moles divided by volume to get a concentration of ammonia. Now we want to find out the moles of ammonia. Moles is equals to concentration times by volume, and I'll just put NH3 just to clarify what I'm finding the moles of, which is going to be the concentration 0.02166 times by 0.150, and volume is already in its correct unit, so we don't need to convert it. So my answer times by 0.150, and I get 3.25 times by 10 to the power minus 3. Apologies because it's pretty messy the working out, but hopefully, because I've spoken through it and gone through it, hopefully you understand it now. Find out, write the expression for Kc, rearrange it, find ammonia, substitute the values in, you get ammonia as that, NH3 is that, and then therefore you can find out the, now we find out concentration of ammonia, then we can find out the moles of ammonia, moles of concentration and volume. 0.02166 times by 0.150, 3.25 times by 10 to the power minus 3 moles. And then 7.5, calculate the value at 745 Kelvin for the equilibrium constant Kc for this dissociation of ammonia to give hydrogen and nitrogen. State the units. Well, it hasn't given us, usually when it wants you to calculate equilibrium constant Kc for another reaction for 2 marks, it's a bit of a trick that the only way you would know really is if you expose yourself to it in pattern recognition. So if you look at this equation and this equation, aren't they the same? 3H2 plus N2, 2NH3, 2NH3, 3H2 plus N2. What we've done is we flipped it over. What's on the left hand side becomes on the right hand side, and then what's on the right hand side becomes the left hand side. So what we're going to do to find out the Kc for this, so it's just going to be 1 over the Kc for this reaction, 0.118. 0.118. It's a bit of a tricky question, but now if you guys haven't seen that type of question, this type of question before, now you've seen it, and yeah, so now you know next time. And then state the units. Well, the units, same thing. The units is just going to be, for this one, we just flipped over the reaction. The unit's going to be flipped over. It's going to be 1 over the units for this one. Well, the units for this one was mole to the power, I can't really see that, mole to the power minus 2 dm6, I'm pretty sure. So mole to the power minus 2 dm to the power 6. So therefore the units, 1 over, is going to be mole to the power minus 2. It's going to be mole to the power 2 dm to the power minus 6. So just do the opposite, mole to the power 2 dm to the power minus 6. And not the opposite, all we did was what was positive became negative, and what was negative became positive. Mole to the power 2 dm to the power minus 6. And that is the end of question 7.